Now that we've had a little review of line integrals, let's look at introducing the concept of work stored as a precursor to learning about potential. Let's start with analogy of gravity because, like I mentioned before, we're all experts at the way gravity works. And I'll pick on our friend Sisyphus, the Greek mythological figure that has to push a rock up a hill. Let's just say, for the sake of keeping this a one-dimensional problem, that the hill is very steep and we're just pushing the rock straight up. The main thing that we're trying to calculate is the work that's expended for Sisyphus to push the rock up by a certain distance. That is going to relate to the potential energy that is inherent within this boulder, right? And this potential energy we can then cash into kinetic energy by just dropping it back to its reference point. So when the boulder goes up, you store some energy, and then when it comes back down, you'll be able to convert it into kinetic energy. So we're going to introduce the formula for that, and then later on we're going to look at this in the context of an electric field. So if you're given an electric field that looks just like this gravity diagram here, and you move a positive charge against the electric field uphill into a certain location and store it, that gives you a potential. And then when you drop that positive charge along the electric field back down, you can then cash it into energy that you can use to do work, like light a light bulb or record a not very exciting lecture on work and potential. Let's start with a gravity analogy, or the Sisyphean analogy. In this case, the work stored is going to be equal to negative the integral of force, in this case gravity, dot dl. And remember that this is a one-dimensional problem. Let's just say this direction is y, so our dl is going to be dy y hat, and f, in this case gravity, is going to be equal to mg in the minus direction, right? Minus y hat direction. And let's say that Sisyphus moved it from location 0 to location 10 meters. Worked very hard that day. So then we plug these in. Work is going to be equal to minus integral of negative mg y hat, and dl we said is dy y hat. So y hat dot y hat is equal to 1, and then you have your dy here. And you're integrating from 0 to 10, which gives you the two negatives cancel out, so you're left with mg y evaluated at 0 to 10, which is 10 mg. So you end up with the kind of the potential energy formula, where the potential energy stored is mgh. In this case, h is 10. So that basically is what we want to cover. We just want to, instead of just using force, we're going to be looking at the force due to an electric charge in an electric field. If you have an electric field E, and then what's the force that a positive charge or a charge Q would find? So the force that you would have to exert to move the charge is the force that the charge is experiencing, that you have to fight against to store energy, is going to be QE, right? So in this case, we're going to put in QE in here, and then everything else stays the same. You get the relationship that the work stored by moving a charge Q is going to be the line integral of E dot dl, where this is the start. I'll call this the initial and the final position. So note this minus sign in both of these places. That's kind of saying that the textbook, you might see if you're reading the textbook says that work is equal to negative QE, which can be a little bit confusing. But what it's saying is, I kind of incorporated the negative sign outside in my definition. So what we're saying is that in order to store energy, you have to be moving against the field. So you can look at it two ways. You can look at it, so I'm just using this formula where I have the negative sign in here, the negative meaning that you have to move against the field. another way to view it is the way the textbook describes it is in order to store energy, you're moving against the field. So they put the negative sign in here, but then don't take that into account out here. So it's not the same as the textbook, but I think that this way makes a little bit more intuitive sense to me, to just always have the negative sign out here and say you have to move against it for it to count. Because if you're not moving against it, then it's actually the field that's doing the work, and you're cashing in energy, not creating stored energy. So this is the main, regardless, the end result is the same. If you're trying to calculate the work performed, or I like to just think like in terms of calories burned when you're trying to move a charge, it's a line integral, initial, final, with a negative sign outside. The one thing that I want to point out is that this is path independent. So when I'm trying to calculate the potential energy, you kind of see this when you're in Newtonian physics with gravity as well, right? If you lift the rock all the way up to 20 and then drop it to 10, or you drop it to negative 10 and then move it all the way up to 10, the amount of total energy is the same, right? If you went up and went back down, you kind of store more and then cash it in immediately. So in the end, it's really path independent. You just worry about the beginning and the end point. So the earlier, fortunately in this case, the earlier discussion about needing to follow a certain path, that doesn't apply for the purposes of calculating the work done or the potential energy stored. And one way to say that is that the field in this static case is conservative. So a conservative field, I also want to define this term. A conservative field is the same as saying that it's path independent for purposes of calculating things like work. So examples include gravity in our description here. You can lift it. If you go uphill and downhill and uphill again, when you're calculating the amount of potential energy you gained, it's really just the starting and end point. The other thing, we said that's the same with electric fields, but to further clarify, it's the case for electrostatic fields, meaning it doesn't vary with time. If the field varies with time, then it may have cost you calories to end up where you started, because the field might change. So the gravity analogy for an electrodynamic field is, you're riding your bicycle and it starts out like this, right? You go from point A and then you get to point B, and to do that you created some MGH, right? And you feel good about that. But if the field was changing, that's like saying the terrain changes over time. So that means that if you went from, say, while you're traveling, the terrain changed, and even though you're in the same location, your altitude is now different, right? So even though you went from point A to point B, and at this time t=0, you would have had to do work and create energy. If the terrain changed and at t=t1, it looks like this, then you didn't actually have to burn calories. You actually expended you actually did negative work, right? You cashed in some kinetic energy in this process. So an electrodynamic field would be how, elder generations can say they walked uphill both ways to school, right? Whereas this is our situation here, where presumably we're going downhill both ways to school, meaning that the relative altitude of our home and school changes over time. So the key point of all that is to just help you remember that fields are only conservative when it's electrostatic. Another example is where we kind of see conservation is Kirchhoff's voltage law. When we're solving DC circuits, or when we're solving the voltage at a snapshot in time, remember that if we have a voltage source here and a resistance here, if we just look at all the potential changes across a closed loop, the gains and losses will be equal to 0. So that's another. So the application of Kirchhoff's voltage law is also another way of saying that that the voltage calculations in a circuit is conserved. So to recap, we kind of used a gravity analogy to introduce the concept of work performed, and then extended that to electric fields. But the bottom line is that if you're trying to calculate the energy stored by moving a charge, the formula is this, right? It's the line integral of E dot dl from the starting point to the final point times the charge, because QE is the force that you're fighting against, and with a negative sign because you have to move against the force in order to be storing energy. And then the other thing is we introduced the concept of a conservative field, which means that it's path independent, and you can throw out a lot of the more challenging steps when doing a line integral. You can just integrate from the starting point to the ending point.